start a new chapter. It's actually chapter 3 in your textbook, especially 3.1 and 3.2 and I think 3.3, section 3.3. It's all about algorithms. So I'm going to give you some basic idea about algorithms, and then I will talk about the growth functions, algorithms. Can anyone comment if everything is visible?
Yes.
Yes.
Okay, thank you. So algorithms. So first of all, actually, algorithm. What is algorithm? If you want to make any food, say you want to make uh, some curry or something, so you need a recipe, right? So similarly, for solving a problem, you require a recipe how to solve it, right? And I think there is a systematic procedure through which you can actually arrive at the solution to some of the problems. So algorithms word actually is popularized by the Arabian mathematicians, but of course these things were known earlier in India as well, but anyway, and I think as I told you, the first thing that you need to look at if you really want to learn the subject is the book Art of Computer Programming. I am again mentioning this by Donald Knuth. And this book is in several volumes. So I think some of the algorithms what we are going to discuss today are from this book only, but there are plenty of different kind of algorithms given for doing different things. So if you really want to learn programming or computer science, you need to look at this book seriously. I mean, you should have all the volumes on your desk. You should purchase it and have it and read it, execute it, and then you will shine like anything in the area of programming. Okay. So the first algorithm that I would like to discuss is finding a maximum element. I'm just saying algo 1 I would like to describe now, and it is all about finding a maximum element in a finite, less than infinity means finite sequence. If there is a finite sequence of numbers, I have to find the maximum element. So I'm just writing what is known as pseudocode. I think some of you might be familiar with this, but anyway, for the completeness, I have to write procedure maximum of a1, a2, an. These are integers. Okay. And then we assign maximum as a variable with a1, and then for I is equal to 2 to n, if maximum is less than ai, then obviously this will be the new maximum, right? Then we assign maximum as ai. So basically maximum is the largest element. Okay, so this whole thing is known as pseudocode for finding maximum element. This is known as pseudocode. Okay, so the thing is that how this works, basically there are certain properties for any algorithms. There are about 7 properties that we should check all the time, and so we are going to look at this algorithm. So I think it is clear to you, right? Procedure is maximum. So input is a1, a2, an are integers which are input to the system, and then we start with a max variable. We assign the first entry a1, and for each I is equal to 2 to n for the next row. So we are checking numbers a2, a3, a4 up to an, and if I find a number which is bigger than this max variable, then I replace the max variable with that number, right? And this, if you keep on doing this, ultimately you will find the maximum number, right, out of all these inputs. So basically, what are the properties? So let me describe some basic properties, and we can check that these properties hold for this algorithm one. Okay, 1 minute, I think. Okay. So the first property, one minute, I think I should. Okay, fine. So this is the so let us look at these properties one by one. So the properties I am writing now. So in practice, we don't do this quite often, but at least we know. I mean, we do check them. The first thing is that each algorithm has an input, right? So we know that in our case, it is sequence of integers. Okay, sequence of integers are our input. Okay. Second thing that you note, so as you can check that sequence of integers a1, a2, an is our input to the algorithm, right? Second, there should be an output. So we can check. So output will be the largest integer in the sequence, right? That is the output of this algorithm. Fine. Next, third property, there should be definiteness, of the algorithm. So that means we are saying that each step is precisely defined. Each step is precisely defined. So we know that here the descriptions in the algorithm are as only assignments, right? A finite loop, and conditional statement. Okay, these things only occur here. So each step is precisely defined as only assignment, a finite loop, and conditional statement, etc. So there is a definiteness. Fourth is the most important one, which is the correctness of the algorithm. Correctness of the algorithm. So in order to show the correctness, okay, we must show that that algo terminates the value of the variable max equals the maximum of the terms of the sequence. right? So this max variable equals the maximum of the terms of the sequence. So we need to show that the correctness, we must show that the algorithm terminates the value of the variable max. So you check that max is a variable, right? And equals the maximum of the terms of the sequence. So initial value is the first term a1. As you can check that the initial value of the max variable is a1 here. The initial value is a1, right? And as successive terms, from when we are applying this loop, we are actually checking the successive terms, right? If the term exceeds the maximum of the term previously examined, you know so we what I'm saying that, so now, so initial value is the first term a1. As successive terms are examined, maximum is updated, right? This maximum is updated here, this update is done here, right? So whenever the max is there, so we update the maximum term, right? So to the value of the term, if the term is exceeds the maximum of the term previously examined, therefore when all the terms are examined, maximum is equal to the value of the largest term, right? So basically this algorithm is correct. Okay, so correctness is there. Okay, next property is finiteness. So which is there, we know that the algo uses finite number of steps. Less than infinity means finite. Okay, finite number of steps. So this is also there. Number 6, effectiveness. Okay, that means the algo can be carried out in infinite amount of time, as each step is either a comparison, you are comparing, right, or an assignment, right? So this is algorithm is effective. 7 property, the last property, generality. Okay, the algo is general as it can be used to find maximum of any finite sequence of integers. This is quite general, right? It is not that it's going only to work for certain set of integers. For any set of integers, as long as they are finite, we can find the maxima, right? So all these 7 properties holds for this algorithm, right? So the first one is input. Of course, there is sequence of integers. Output, yes, the largest integer in the sequence is the output. Okay, then definiteness is there, each step is precisely defined. Fine. Correctness, in order to show the correctness, you must show that the algorithm terminates the value of the variable max equals to the maximum of the terms of the sequence. That is also there, right? Fifth, finiteness, the algorithm uses finite number of steps. Effectiveness and generality, right? So these are the basic things for the algorithm. So now actually I am not going to discuss these 7 steps all the time for all the algorithms, but I think you can verify that this is true whenever we are discussing any algorithm, right? So I think as an exercise, you can just check when we are going to do for different algorithms right now. So let me actually now talk about, so this was finding a maximum element in a finite sequence of integers. Now I'm going to give you another algorithm, searching algorithm. Okay, so there are different kind of searching algorithm. First I'm going to discuss linear search. So searching algorithms, right? And the first one we are going to discuss is linear search or sequential search. Okay, so this is the linear search or sequential search algorithm. What is that? So again, I am going to write the pseudo code. Okay, so this is a bit straightforward actually algorithm. Procedure linear search, right? So x is an integer that we want to search, right? That is one of the input, and we have a sequence of integers a1, a2, an. These are distinct integers. Okay, so x is given and all these integers are given a1, a2, an, right? So I have to search x in this. So what I do, I initialize I is equal to 1 index, while I is less than or equal to n and x is not equal to ai, right? Unless we find a search, right? We keep on increment I as I plus 1, right? If I is less than or equal to n, then location is I, right? Else location is 0. So location is the subscript of the term that equals to x. Okay, so if we match is found, so that location is I, which location it is, right? Otherwise it is 0. So location is, I should mention it here, location is the subscript of the term that equals to x or is 0 if x is not found, right? So this is a very basic thing. You just doing it linear search, right? Okay, pick up the first element. Okay, is it x? If yes, fine. Location is subscript 1 is given. Okay, this location. If not, you move to the next one and so on, right? So this is the linear search. It's fairly straightforward algorithm. I'm going to describe another searching algorithm which is a little bit better than this actually. So let us do this, known as binary search. This is quite popular algorithm. So binary search can be used when the list has terms in the order of increasing size, right? Or lexicographic in case of words. Okay. So we are assuming that the list, that all the terms are in the increasing order. Let us take an example. We understand the example, and then I'll give you the pseudocode. Okay. Search for 19 in the list. And list is 1, 2, 3, 5, 6, 7, 8, 10, 12, 13, 15, 16, 18, 90, 20, 22. I have to locate 19. So how many integers are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There are 16 integers here, right? Okay, and I have to locate 19 in this list. So what I do, as the term indicates, binary search. So what I'm going to do, I will divide it into half. So I split it. So I'm splitting it here, nearly half of it, right? And then this is what is called as first split. I split the list in half. One half this side, another half this side. And then, so basically we have 1, 2, 3, 5, 6, 7, 8, 10, and on the other side we have 12, 13, 15, 16, 18, 19, 20, 22. Right? And now I check this number 19 to the maximum here, here it is 10, right? So as we know that as 10 is less than 19, so 19 is bigger than this number, we leave this and we choose the second list, right? Okay, so we choose this list. Now this list has 1, 2, 3, 4, 5, 6, 7, 8 numbers. So I again split it at this place, right? I again split it here. So two splits are 12, 13, 15, 16, then 18, 19, 20, 22, right? Two splits. And again check with the last number. So as 16 is less than 19, I leave this list and I choose this second list and again split it at this place. And now two lists are 18, 19, right? And 20, 22. Now 19 is less than or equal to largest term of first list, this one. So I choose this. I discard the other list. Okay. So basically we are left with 18, this list 18, 19, and I again split it here. Okay. So as 18 is less than 19, we choose second list, right? And search is now narrowed down to one term. Now only one term is left. Comparison is made for one term, and so bingo, 19 is located. Okay, as 14th term, right? So this is how we do the binary search. So all this, whatever I told you, so I think again I just show you. So 19 we need to locate. We divide it into half, first half, second half, and then we compare, right? The final one, the largest one, we compare with the number 19. Okay, so the first list is not needed. We go to the second list, again split, and so on. We doing this. Finally, we narrow down it to 19. So whatever I told you, so in general, actually, to search X in A1, A2, and AN, where it is known that A1 is less than A2 and so on, less than AN, we begin by comparing X with middle term of the sequence. AM, where M is basically greatest integer n plus 1 by 2, because in case if it is odd, so this number will give me the middle. Okay, so keeping this in mind, I can write down the binary search algorithm, pseudocode for the binary search algorithm. So we have procedure, binary search, X as integer, and A1, A2, AN are in increasing order. increasing integers, right? So we initialize I is equal to 1. So note that I is left endpoint of search interval. I is the leftmost point, fine. And j is equal to n. So j is right endpoint of search interval. Okay. So while I is less than j, begin m is equal to critical I plus j by 2, right? If x is greater than am, then I is equal to m plus 1, else j is equal to m, and if x is equal to ai, then location is the output I, else location is 0. So I think it's now fairly straightforward how to do this. Now I would like to tell you that as an exercise, you please write a program for doing these things. Exercise. Write a program for all these algorithms. Either it is in C, Java, Python, whatever language you want. You just implement these algorithms, right? So that you will have some better idea. So this is all about binary search algorithm. Now,
Hello, sir.
yes.
Sir, here if x is equal to am should come. That if x is equal to ai, we are comparing with middle term. So if
Yeah, we
middle
are. Yeah.
term, so if middle term will become equal to x, then
Yeah. So then that will be the point, right? So here you see in this case, in this last one, right? You see 18, 19 was there, right? When we compared here. So so final term is comparison made is equal to equal, right? So then you found the term, right?
so
Right?
sir, here my question is why x is equal to ai? Should x is equal to am will come, no?
No. So I'm saying that because there is a loop, right? There is a loop here, right? M is the middle term,
Yes.
right? There is a loop here, ing. You see, those are variables, right?
Yeah.
So
Yes, sir.
yeah, it can come anytime, anywhere, right? So it can come, sometime at the end point or sometime somewhere else, So there is a loop here. Okay, so now I think I would like to describe what is known as sorting algorithm. By the way, sorting algorithm is very popular for interviews also. People ask a lot of questions about sorting. I think if you give a job interview or something, they are going to ask you these things. So where to study these things? I should tell you that Donald Knuth book, there are about 400 pages, 15 different sorting algorithms. Unfortunately, I'm not going to cover all of them here, but I'll just mention few of them. So you can actually look at the book by Donald Knuth, right? And look at all these 15 sorting algorithms. I'm going to describe two of them. One is bubble sort, another one is insertion sort. And I think, yeah, that's all. So let us see. First is a bubble sort. As the name suggests, there is some sort of bubble, right, when we are sorting it. So let us write down the pseudocode. Procedure, bubble sort, A1, A2, AN. These are real numbers with At least two of them are there. N is at least 2. Otherwise, how we'll sort? For I is equal to 1 to n minus 1, and for j is equal to 1 to n minus I, if aj is greater than aj plus 1, then interchange. Okay, so the lowest index is bigger than the highest index, right? So just interchange. It should be in that order. Interchange aj and aj plus 1, right? So finally, a1, an in increasing order, right? So let us take an example. So it will be really clear how this bubble sort works. Okay, so let us take an example. Sort 3, 2, 4, 1, 5. So there are 5 numbers 3, 2, 4, 1, 5 into increasing order using bubble sort. So what I'm going to do, I'm going to write 3, 2, 4, 1, 5. Okay, and I'm going to do first pass. So what I'm going to do, I'm going to compare starting from the first one, right? And just compare this and this. So either they are basically increasing order or they are not in increasing order. So as you can check, this is not an increasing order. So we interchange the position of this and this, right? So we will get 2, 3, 4, 1, 5. So this is done. Now we check the second. Now we check this and this. Since these are in increasing order, so we are not going to make any change. Okay, so we leave it as this. We go to the next one. So in the next step, 2, 3, 4, 1, 5, and we compare again 4 and 1. As you can see that it is not in the order, so I just interchange 4 and 1, right? Next is 2, 3, 1, 4, 5, and then again we compare the last one. So as you can see that they are in the order, so we are not going to make any change. So this is the first pass of the algorithm, right? What we did, starting from the first one, then go to these are the small bubbles, we can say. That's why it is known as bubble sort, right? We just do the 3 and 2 and then 3, 4 and so on. So we are left with this. Now second pass, I'm going to again start from the first one. So basically, I think maybe I can write it down here. Second pass. As you can see that we have 2, 3, 1, 4, 5. That's the last one we have. And we compare this and this. So 2, 3, there is no issue. So we leave it as it is, unchanged. Then we go to the next one. So it is 2, 3, 1, 4, 5. And now we need to interchange 1 and 3, right? Okay, because they are not in the order. Then the rest, what we get is 2, 1, 3, 4, 5. Okay. So in this pass, I go to the next one, no change, right? And we are done. And 4, 5, of course, there is no change, right? So now in the second pass, we left with this sequence 2, 1, 3, 4, 5. Go to the third pass. Third pass of the algorithm. Okay. So we had 2, 1, 3, 4, 5, right? So starting from this, we again need to interchange. We are left with 1, 2, 3, 4, 5. Okay. So basically, we are left with fourth pass. We are left with final answer. You can see that no matter if we keep on doing this, there is no change anyway, right? So it's kind of fixed. So final answer we are left with after fourth pass is this. So it's in the increasing order, right? So basically, this is the fourth pass, right? And then everything is in the order. So this is how we do the bubble sort. Okay. So essentially, if pair are, we put this kind of symbol if pairs are in correct order, right? And we put this kind of symbol when we are interchanging. That's what we did all the time. Okay. So this is all about bubble sort. Now, the next algorithm is what is known as insertion sort. So slightly different way it operates. So I hope the bubble sort is okay to you. Now we'll talk about insertion sort. So by the way, these things are again and again, I'm telling you, very, very important for your interview also. Interview people, if you go for Google or any Facebook or interview, they are going to ask you questions on sorting algorithms if there is a technical round of interview, right? So just try to see how many sorting algorithms you can learn, searching and sorting. These are two very basic things. Each computer scientist should know these things. Okay. So I'm going to write down the pseudo code for insertion sort. Procedure insertion sort A1 AN real numbers with n greater than equal to 2, fine, for j from 2 to n, begin I is equal to 1, while aj is bigger than ai, I equal to I plus 1, m is a new index with aj, store aj, for k is equal to 0 to j minus I minus 1, a j minus k is aj minus k plus 1, aj is equal to m, and is a1 a2 an sorted. Okay, so this is the pseudo code for insertion sort. Again, I think I should give an example so that you can really understand how this works. Okay, insertion sort example. So elements are 3, 2, 4, 1, 5. The same list I have taken. Now I'm going to use insertion sort to sort them into increasing order, right? So what we do, first compare 2 and 3. Okay, as 3 is bigger than 2, place 2 at first place. Okay, so this will be 2, 3, 4, 1, 5. Okay, now we move to the next number, which is 4. Okay, so compare 4 with 2 and with 3, both. This is the difference you see between the bubble sort and insertion sort. Now we are comparing with all the previous numbers here. 4 is compared with 2 as well as 3. As you can see that 4 is greater than 2 and 4 is greater than 3. So 4 is placed in the at third position, right? So we have 2, 3, 4, 1, 5. So list is not changed actually, right? Now compare the next number 1. Compare 1 with 2. 1 is less than 2. 1 is less than 3 and 1 is less than 4. Therefore, 1 is placed at first position, right? Because it is less than all of them. So the list is 1, 2, 3, 4, 5. Now we look at the last number, 5. As 5 is greater than 4, so it goes to end position. End position. So the sorted list is 1, 2, 3, 4, 5. Okay. Okay, so this is how. Here we were comparing 4. Okay. And then we were comparing 1 here. And then we were comparing 5. So this is how we do the insertion sort. I think so. As I told you, there are 15 different sorting algorithms. You should try to learn as many as of them, and you should also study their complexity. So, in fact, what is complexity? I'm going to talk about complexity in pretty soon, in terms of what is a growth function and so on. So, one last algorithm which I would like to mention, but maybe I will not give much details. Let me show you which is known as greedy algorithm. Greedy algorithm is is pretty straightforward. Suppose you want, I'll give you an example. Okay, suppose you want bunch of vectors. So suppose n and d is given. What is n? N is the length. So suppose we are given 1 1 1 1 0 1 1 0 0 1 1 1 1 0. Right. Suppose this set is given with these vectors. So length is given. Sorry, n is 4 here, right? And suppose d is given as 2. Okay, d is given as 2. D is what is distance. So I just want to, so I can take another number 1 0 1 0. Another vector is there, say, or 1 1 1 1. Another vector is there. So I need to put all these vectors in such a such that d is maximum, 2 is achieved. So what I do, so what is d? D is the distance between two vectors. So you can check that these two vectors, the distance is 1 1 only, right? Here the distance is 3. Here the distance between these two, number of places they differ, 1. Okay, and here the distance is 2. So I need to make greedy choice out of this set. So basically, if I have to create a set of n is equal to 4 such that d is equal to 2, so basically what I should do, I should write down all 16 vectors of length 16. So 0 0 0, or maybe I should take length 3 here so that I can demonstrate here. 0 0 1 0 1 0 1 0 0 1 1 0 1 0 1 0 1 1 1 1 1. Yeah, all 8 vectors are given here, right? And I need to somehow, so and I can simplify. I think I can do this. N is equal to 3 here and d is equal to 2. I want a set of vectors of length 3 and with distance 2. Okay, so I start, the greedy approach says that I start with the first vector from this list. Can I put this vector here? Well, the distance, the weight is 0. Basically, there is no 1 here, so I will discard it. Or sometime if you want linear space, I can put it here, but like now I can discard it. Or suppose I put it here, no problem. Then can I take this vector 0 0 1? If I put 0 0 1 here, 0 0 1, so distance between them is 1. I want distance 2, so I cannot take this. I go to the next one, 0 1 0 0 1 0, distance from this one is 1, so I cannot take this. I go and pick up 1 0 0. 1 0 0, again distance between them is 1, so I cannot take this. I go to 1 1 0, that vector I can take because the distance between them is 2. Okay, this vector I can take. Now the next is, can I take vector 1 0 1? 1 0 1, distance from first vector is 2. 1 0 1, 1 0 1. So this vector has distance 2 from here and also distance 2 from here. D is equal to 2 is equal to, so I can take this vector. Then I go to the next vector 0 1 1.
Hello.
Yes.
Hello. Hello.
Any question?
Hello.
Any question? Any question?
Sir, I had a question, sir. Here we are talking about Hamming distances, right?
Yes, Hamming distances, right.
Okay, sir. Yes.
So what I'm doing, I'm making a greedy choice. You can see that. I wanted to construct a set where the length is 3 and the distance is 2 always between all the vectors, right? So I'm trying one by one. From all possibilities, I'm putting the vectors by making a greedy choice. Okay? So that's why I'm
Yes.
giving you. Yeah. So 101 is. Yes.
I was just saying that because we are checking with all the possibilities, that's why it is called greedy algorithm, right?
Yes. So we are just making greedy choice. And actually, choice is always a greedy, because what I want, I am only choosing that. Rest I am not worrying about, right? I am dropping them. Right. So 101 is there. Next, can I put 011? 011 distance from here, it is 2. Right. 0. If I take 011, can I take it here? From here distance is 2. From here again distance is 2. And from here again distance is 2. So yes, this will work. But can I put 111? 111 distance is 3, which is fine. But 111 distance will be what? 1. So this is not going to work. So this is our set. So by greedy choice, always I'm making a greedy choice, right, to construct the set. So this set has n is equal to 3 and d is equal to 2. The Hamming distance between the vectors is 2 always, right? So this is a greedy algorithm. So any question at this point? Otherwise, I can talk about now the growth functions. Something about the growth functions. So these are actually some algorithms I covered. I have not covered all of them, as I told you. The best book is Donald E. Knuth, Art of Computer Programming, which you should have on your desk. If you really want to learn computer science, you should buy volume 1, volume 2, as much as you can understand. Believe me, the people, I should tell you, people who have studied this book in my course earlier, right now their package is 1.25 crore. You see, because they understood the book. So they are the technology hero right now in the companies, right? So as I'm telling you, it's very, very important to read that book. Okay. So I think there is some problem. Please mute yourself. Please mute everyone. Anyway, so okay, so next let me talk about growth of functions. So many times when we are actually trying to study the algorithms, I would like to know how much time they are going to take in terms of number of steps, and we can compare them, which one is faster, which one is slower. For example, the sorting algorithm, right? I would like to ask which one I should use, insertion sort, bubble sort. So I would like to know what is the complexity, or how much time it is going to take. So the growth of functions actually is a old topic, and I think a very nice book if you really want to study them in details is Order of Infinity by G.H. Hardy. He's a famous mathematician. So if you want, you can look at this book by G.H. Hardy. Okay, it's a very good book where you can study the growth of the functions. Some of you, if you have done a serious calculus study, you might have encountered this, growth of the functions. Anyway, so I'm going to talk about what is known as big O notation. Okay, the big O notation. So suppose f and g are functions from set of integers or reals to reals. So domain is either a set of integers or reals, and the codomain is reals. We say that a function f of x is big O of g of x, big O of g of x, if there exist constant c and k such that mod of f of x less than or equal to c times mod of g of x whenever x is greater than k. Okay, c is known as Borel constant, name of a scientist, Borel constant. So that means it's saying that the absolute value of f of x cannot exceed constant times absolute value of g of x whenever x is exceeding certain fixed number k. Okay, so that means whenever x is approaching towards infinity, actually the growth of the function fx behaves as the order of g of x, right? So it is, the absolute value of f of x is less than or equal to c times g of x. Okay, so let me give you one or two examples, and I think that will be good. Example is f of x is equal to x square plus 2x plus 1. So I'm saying that this is big O of x square when x is greater than 1. So remember, whenever we are saying function f of x is big O of x square, we are also mentioning the value of x, how it is changing, right? So we know that 1 is less than x, right? From here, this implies that x is less than x square, right? Now this implies that f of x, which is equal to x square plus 2x plus 1, is less than x square plus 2x square, because x is less than x square, plus 1 is less than x. So this implies that x is less than x square, and also we can say that 1 is less than x square. Yes, so the whole thing is x square, so overall thing is 4 times x square. So that means our constant c is equal to 4 and k is equal to 1, right? In the previous definition, as you can see, that c is equal to 4 and k is equal to 1. Therefore f of x is big O of x square. Okay, right? So another way of doing it, I mean, there is an alternate way. I mean, there are different ways you can do it. Alternate way is, so when when x is greater than 2, of course if x is greater than 1, it will be greater than 2, right? This implies that 2x is less than x square, and 1 is less than or equal to x square anyway, right? So f of x is equal to x square plus 2x plus 1 less than or equal to x square plus x square plus x square is equal to 3x square. In this case, c is equal to 3 and k is equal to 2. Okay. Okay. So this is one way of looking at these things, right? Let us take some more examples. Can I say that x square is big O of x square plus 2x plus 1? Now, since x square is less than x square plus 2x plus 1, when x is greater than 1, right? So here c is equal to 1 and k is equal to 1. So this is true, right? So these kind of things are possible. Let us take another example. 7x square is big O of x cubed. So when x is greater than 7, right, this implies that 7x square is less than x cube. Therefore 7x square is big O of x cube. Here c is 1 and k is equal to 7. Right. So these kind of things are possible. I think I will stop at this point. If you have any questions, you can ask. Otherwise, we will talk more about the growth functions in the next class. Any question?
Sir, for this case, we can also say that 7x square is a big O of x is to 4, right?
Yeah, so by choosing the value of x, you know how you are choosing, you can actually show that, right? So basically you have to find c and k, appropriate c and k to show the behavior, right?
Yes.
Yes.
So means a particular function may have many big O notations.
Correct.
So which will be the best notation for that?
That depends upon when we are working with the applications, right? I mean, so actually now think something like this. Have you heard of Taylor series?
Yes, sir.
Yes, sir.
Yeah, Taylor series. So you remember the reminder is always in the form of big O of something. You know, if you remember. Have you used that
Yes,
notation?
we added function at the last.
Yes. Yeah. So see, depending upon how many terms you want, you can keep on changing the order, right? You know, you can you know you
Means
can
it
move.
depends on the accuracy which we want, right?
Yes. It depends on the accuracy how much you want. Correct.
Yes, understood, sir. Thank you, sir.
Yeah. So I think so. This is a very nice area, and I think this is also I should tell you that for interviews, this is also a very important topic. They also ask you this big O notation, and many times people don't know what is big O, small o, and so on. So there are big O notation, small o notation, and big theta notation, right? So I'm going to talk about these things more in the next class. But please do look at chapter 3 of the book. Okay, read chapter 3 of the book. Most of the examples I am taking now from book only. I'm not going anywhere outside the book now. Okay, so you can really find it interesting reading the book, doing the problems, and of course assignments, homework that will be given to you. Okay, so I think that's all. So thanks. So I will be closing the session now.
Thank you, sir.
Thank you.